So welcome. This is a special session about memory design in integrated circuit within selected topics of advanced chip design, advanced analog chip design. My name is Johannes Fellner. I'm from AMS Osram. AMS Osram is working as design company, a special focus in optical globally. And my part is working in design environment. So especially in corporate IPs. And in corporate IPs, memory is always a topic. So this is where I can give you some background about memories and how to integrate them, and the special topics in the industry about memory, non-volatile memory, and all kind of. So just some quick words about AMS Osram. As said, AMS Osram is a global leader of optical systems. Osram should be a brand name which you should know. So Osram is leading in the emitting world. AMS, which was former AMS Legacy, is part of optical sensing. So here's a good combination of these companies, emitting and sensing. And as said, design is the main topic of sensing with special process nodes and special design techniques. So about memory designs of integrated circuits. So I will give a quick overview of different types of memory, so some theoretical background, how to use memories in integrated circuits, design implementation, analog and digital. So it's a block which can be seen on the one side as digital, but on the other side the development is mainly analog. I will show you later the differences. Volatile memories like static RAMs, latches, flip-flops, but also non-volatile memories like OTP and EEPROM. I will come to this definition later. And the second part is more from the practical side. So to show you the concepts, what we're using, comparator circuits, how we do, where we can do some inventions, what are the tricks around circuits, which elements you can use. You always have to tweak which elements you can use from the shelf, so which is already available, or if you want to develop dedicated elements which are with the main focus on memories. And of course, coming with that is reliability issues about quality, data storage, how long can you store some bits, and so on. So the first part, as said, is the first part is a short overview. So what is the easiest way of doing a memory? It's flip-flops. I think everyone knows flip-flop. Just call it latch is the even easiest one. So having a feedback coupled two inverters with a feedback coupler, and then maybe two latches with a master-slave system. You can then integrate and create a flip-flop. So this is the easiest way. This is always available in standard digital logics. So you can use several flip-flops also to build columns, rows, and build up a memory. It's also straightforward, but of course, flip-flops are consisting of around 20-24 transistors. So area is always a topic for memories. So at a certain size of memories, you start changing, and as I said before, a latch is just two inverters cross-coupled, and just use this more or less for data storage. So it's 6 transistors, then you add 2 additional transistors for switches, and you have a 6 transistor RAM bit cell, which you then can generate and repeat and generate larger memories. And for that, of course, you need some columns and row decoders and to select the different memories inside the whole area. And depending on the availability, what you need to do is, of course, depends. If you always have supply on, you can store the data. It's always stored actively. Typically, a latch is losing information if supply is switched off. So therefore, you have to move from volatile memory to non-volatile memories. And in the full integration of a memory, you even tweak process nodes. So process node in the CMOS world is dealing with special devices. So each transistor is optimized, transistors, resistors, capacitances. You have a backend where you connect this. So this is all part of a integration in the process node, so silicon process node. And for memories, you can optimize your transistors to be able to get smaller and smaller in terms of area, for example, or to have special layers where you can reduce voltage just to store information, or some floating gate techniques I will show you later then. And coming for this is, of course, you all know these big memory sticks. This is mainly process nodes, which the only intention is to tweak the process node to get really just memories. And therefore you have huge kind of memories. You build up not only one layer, typically you have several wafers stacked together to a big area. Otherwise you could not come to gigabytes. But this is a totally different topic. I will not talk about that. So a little bit of theory about how to cluster memories. So I want to cluster it on one side from the chip individual use cases. So to say, what do you intend to use memories? So one idea would be a serial number. So to identify chips or let's say link hardware together, you need serial numbers. This is of course a permanent storage, so you need OTPs. So this is a non-volatile approach. Trimming code is always one of the main used fields for memories. Here is also permanent, the use case. So this is, of course, each transistor has a certain variation over the process. And sometimes this variation gives you a lot of headaches for simulation, if you have worst case simulations. If you want to create an oscillator at 10 megahertz and you get a spread from 5 to 20 megahertz, this is nothing you can use. So when you need to, let's say, rearrange or re-optimize transistor values, absolute resistor values, for example, to get back to your nominal value. So this is trimming, for example. Data locking, this is also a technique what you want to use sometimes. For some measurements, you want to store the measurements permanent, let's say counting up or doing data locking for certain events. This is all permanent. Microprocessor systems, here we are entering the field of RAMs. So this is more volatile. So you always change the code. You can copy it in from wherever, either from a permanent memory, flash, whatever, and run the code, or from an internal ROM, which you use then. And this is because you have to change the code. It's a microprocessor, wants to change code, wants to multiply and set back data. So it has to be volatile. So you cannot deal with always reprogramming or fixed programming. And then digital registers for individual system settings. This is, of course, also volatile, so this is register. Sometimes you want to switch from one back to next, or switch on and off features, but this should be also selectable. And then we have, so this is more or less the first part was from the chip side. And then of course you have the system use cases. So analog features, you want to use some code for analog features, trimming, switching on and off, amplifications of other topics. Then digital registers, of course, as said before, code and multiplying and doing any kind of combination of digital information. Firmware for microprocessor systems. Here we are also from the user side, but this is more or less sometimes what you want to upgrade, and this should be permanent because firmware should be the first code which should be installed, and this will not change that often. Application software, here we also have for microprocessor systems. This is the core part where you define your systems. And between this and then code for microprocessor systems. So it could be semi-permanent. Sometimes you even want to, let's say, if you lose your supply, you still want to keep information. So sometimes you always take the disadvantage of writing time, because in hard writing it's always a matter of additional time which you need. But let's say keeping the last information always alive in your system, you use then NVMs. So here in these three last fields what I mentioned, you distinguish between ROM, which you can only program once, you have no chance in your system to change, or non-volatile memory. Non-volatile memory is more or less a memory where you have the chance to influence the data later on. So you are not related to a process or to one mask set which you define the code. You are able to change it later for any purpose. And coming to a comparison of sizes, so as mentioned before, we have here the pointer is this one, starting from flip-flops down to non-volatile memories. Here we do have the flip-flops, as said. These are entering in the few bits. You will not do. You can avoid to have some RAMs, a few bits, maybe 10 flip-flops, 20 flip-flops in a system. But whatever is exceeding this, you should consider using RAMs or register files. And register, you're in the range of a few kilo, up to a kilobit. And then you start from registers, which is more or less also based on clusters of flip-flops, a little bit optimized maybe. You start register file, which is the easiest way to implement a RAM bit cell, for example. And then you have the SRAM, the special optimized RAMs, where typically the process node is also tweaked to use the smallest area for the memories. So you try to optimize this. And this is covering, you see, up to from one bit, from a few bit up to megabits. So here you can be creative. On ROM, there are two different main types what we see, a diffusion ROM or a metal ROM. I will come to this later, how you distinguish between this. But it's the kind of which masks you need to change to program code into the ROM. And then on OTP, you can start trying to use elements, and we distinguish here between fuses and anti-fuses. A fuse is more or less if you have your electricity from home. If you remember what a fuse is could cut your power line for some reasons, for a high power event typically. And this is the way. So typically it's connected, and at a certain event it's not connected. So it's open, and then you can, with this information, you can build a 0 or 1 into a memory. Anti-fuse is the other way around. So at the beginning they are high ohmic, and after, let's say, melting something together, you get the low ohmic connection. It's just, from a digital point of view, you don't care, you just invert it. It's just either you work with zeros or ones or zeros, you just invert them. And non-volatile memory, here we typically distinguish, you can optimize to high reliability. High reliability, you have some techniques where you want to avoid, typically you have something where you have stored some electrons. It's as a basic principle. And you have to ensure that these electrons will stay there forever, ideally, or at least for 10 years. And here you have the key, your key problem here is temperature. The higher the temperature, the more mobility the electron gets, the easier they disappear. And then over time you lose some information. And then of course you still you can do some techniques to increase area and capacitance to hold more electrons inside. On the other side, also you want to build huge gigabyte memories, so you cannot do this with large areas. So you also have to find process tweaks to keep the high density still alive. And what you see here is also in the range from small, a few kilobits or a few hundred bytes, up to megabits. This is the area we're covering. And here we are, as said, just talking about integrated memory on a chip. You don't want to waste too much area. And if you really need much more area, then you go to the external memory and just use latches and just to copy it from outside, just this portion what you need. So coming to bit cell concepts. let's say, a little bit more detail, so at least some schematics. So as said, the easiest one is a RAM. Here we have a 6 transistor RAM. Here these 2 PMOS transistors, 2 NMOS transistors, and 2 switches to the line so that you can change it. What you can see here is also, okay, these 2 transistors build an inverter. The other pair also an inverter, and they are cross coupled. So the one output 0 is holding the input to 0, is driving an output to 1, and this one is holding a 1 here. So it's more or less, once you store it, you have to spend some energy to change the content here to overcome a certain threshold that this is switching back. Therefore, you need some switches and some lines. So these are the world line code. So you then create a memory matrix, and then you can define in which word and which bit line you want to change the content. So you have access, direct access with these 2 lines to any individual bit. So to save area, as said, these are 6 transistor RAMs. To save areas, there's some other techniques. What you want to have is just to keep this alive at 1 or 0, whatever it is. So you could think about of having an ideal capacitance and a switch and store a certain amount of electrons on a capacitor, and you get a certain voltage. Then you can say, okay, it's if you do then the maths, so you can say it's either charged, having a certain threshold voltage on the cap loaded, or it's uncharged, so it's becoming a 0 or 1. It depends then how do you transfer this into digital. Disadvantage of this system is you never get ideal capacitances. So this capacitance will lose content. And over time and temperature, the voltage will drop here, and after a certain time, you will lose your 1 typically. So what you have to do here is, after a certain amount of time, you have to read out this information and, let's say, force it back. So you just increase the voltage on the capacitance. Always before it's lowering to a certain threshold, you still refresh the memory. So that's a dynamic RAM. So it's always running. You cannot switch it off. On the static RAM, once it is stored, you can really lower the voltage down. It will stay always active. You can really lower down the voltage to save power. Then coming to permanent memories. So non-volatile memory. Here the easiest way is a ROM. On the ROM, you see, you just have to connect 2 lines, more or less, nothing less. So either you have a world line and a bit line, and either this is connected somehow via a diode, or it's not connected. And connection, what you see here is these dots are either connected or there's a missing contact, so it's floating. And this means no contact. This line, if you apply here a certain voltage, there is no path to this line. So this line, if you charge it up, will not be discharged. On this side, if you charge up world line 2 and switch on bit line, you will discharge this, and then you can measure on your world line 2 that this is going down, and then you just have to wait a few picoseconds, nanoseconds, however fast your memory is, and detect, okay, now it's going down at a certain threshold. This means it was programmed and it's a 0. So that's the easiest way to do it. Another, this would be a diode as a connection. So what you need to take care here is, of course, why is it a diode, you will ask, is if you have several, a matrix of crossings, you always will find, if you have a diode here and a diode on another line here, you will always find paths from one diode to the next if it is not unidirectional. So you have to you have to allow only a pass of electrons in one direction, so therefore you have to do a diode. If you just would connect it, you would always see from the next line the content. Using this, you can also do transistors. So the transistor you do more or less like coming back to the RAM content what we had before. Then the other side is also seen as you have a gate here. It can be also seen as a capacitance. So you can lower the voltage. You don't have that much current. You just see it switched on or off. So this will can be integrated quite easily. And it's a minimum transistor which you typically use. So the ROM, the size, the minimum size of a ROM bit cell is then defined by the smallest transistor then you can create in this process node. And this is the way most of the ROMs are built in. And as I said before, what you typically do is, easiest way, you pre-charge the line, you wait of a discharge after a certain time, either it was connected or not, and then you have a 0 or 1. So coming to non-volatile memory, you see the content here is a little bit the same like here. So you have a transistor, and what you do is here, instead of switching the drain side of the transistor directly to ground, you use a capacitance. And the capacitance is built by a gate transistor, a gate of a smaller transistor. So you typically in each process, silicon process nodes, you have different, at least typically two gate oxide types. So you have a smaller transistor which can be lowered by threshold voltages down to, let's say, in a 180 nanometer node, for example, 1.8 volt, and then you have transistors in the range of 3 volts. So the physical difference is that this has a thick gate oxide, thick compared to the small transistor. So from reliability standpoint of view, you need much more voltage to destroy this gate oxide than this one. And you use this difference. So you apply here a certain voltage, destroy the gate oxide, and then you have exactly what you had. Either you have a connection to ground or you have it open. And typically it's connected, it's open because it's a cup. It's just a DC side is open. But if you create a breakdown here, then there's a short via the gate oxide, and then it's connected to ground. So this is the difference between the ROM. What you see here is to decide that there is a 0, you have to change a mask. And in this approach, you don't have to change a mask, you just have to apply a voltage, and you can do this already in a processed circuit. So you can change the content after processing. So as I said before, intact gate oxide or broken gate oxide. And again, the same pre-charge circuit, smallest, similar to a ROM. Here we have, in the literature, you will find 1.5 transistor, 2 transistor approach. So what you can do here is in the lithography, you can, we've seen some patents where one is changing directly from the thick oxide to the small oxide. So it's more as a thick oxide with a slightly parallel path on the small oxide. So it's from the topology point of view, it would be 1 transistor with a variation of the gate oxide. And then you destroy the right side, or let's say, destroy the part of the transistor. And the rest is still working. So, other techniques to store information. So this is an easy approach. Here you can also come to quite medium area memories, or medium size memories. Other techniques would be, for example, a Zener diode. Typically, you know, Zener diode in one direction is connected, the other direction you have a certain breakdown voltage. If you exceed this breakdown voltage, you also destroy the PN junction, and then you get the serial resistor or a small low ohmic resistor. This is what I meant at the beginning. It's changing from high ohmic to low ohmic. So it's more or less also one side of, you always do just one side of a transistor, you add something on it. Here you add the Zener diode and change the serial resistor. Nothing more, less like that. Disadvantage of this, the advantage is the Zener diodes, they can be easily implemented. It's standard part of a CMOS process. Disadvantage to destroy this here, you need up to 100 milliamps or even more. So quite intensive current. So also your system has to be able to supply the current in a way. So you need low ohmic paths to certain pads. What the disadvantage of this system is you need high voltage. So if you have a 1.8 volt system, somehow you need charge pumps inside to create, and here we're talking about 5, 6, 7 volts, something like that. Something in between the breakdown of this one and this one. So, and typically 1.8 volt transistors survive 5 volts. So you take 6 volts, at least you exactly want to do what quality doesn't want you to do. You destroy things. And quality always try to find out the maximum voltage which is allowed not to destroy these things over time. And here you have to find a good compromise just to limit your destruction in a certain area and not harm the rest of the circuit. This is always the tricky part if you build in such memories. So having this Zener diode, you could also use other elements instead of a Zener diode. What is available here, for example, instead of a Zener diode, you can use a polyfuse. So what you use then is just a poly line in series to this instead of a Zener diode. So this is a little, I would not say a little bit better, it's much better. You reduce the current here from 100 milliamps down to 20, 30 milliamps. Still quite high current compared, because this is, of course, you could not optimize this because you want the ideal situation is to use the system as is. So what you can use here is a typical poly line, which is the same poly line, for example, on the gate oxide. The poly what you use for transistors. You use it just in the serial way. You don't care about the oxide on the bottom. Just use the serial approach. And you build just thin lines, like really a fuse. And you build thin lines, and you need to exceed a certain voltage to melt this up. So here we're talking also about high currents, but you can define this by, let's say, optimize this by stretching the fuse to, with a minimum width, you can stretch it to factor of 10 length. And then you can get a good spot to melt this down. So it's also intact resistor would be a 0, switched off, and melted is then a high, switched on. So there are typical systems. So the disadvantage of this is the same what I mentioned before on the ROM. You would need something which is allowing you only one direction. So the disadvantage doing this is that for each and any fuse you have, you need one transistor, because there's nothing, let's say, preventing you from using this line connected to this or to the next line and having 2 or 3 polyfuses in serial, and then there has a high current and destroying the other bits also in the same way. Or let's say distributing the current over different bits. So you cannot build here a common line. You have to use here one transistor, and this is a transistor which needs to be able to switch 20, 30 milliamps. So it's also quite area intensive. So the dominant part on the area here is definitely this transistor. So there are ways to overcome this. So by adding a serial diode to this, so you still need this high transistor, but then you can build lines and make parallel approaches, and then define with word line which of these fuses you want to use. So here you can really just have a bit cell which is then consisting of a diode and a resistor or the poly resistor in serial. So here you can more or less build also medium size memories with that. And to optimize this is also reducing the current that you melted up. And there's always a change in resistor values. The higher the change from, let's say, typically a few ohms up to a few kilo ohms, it's easy to build a comparator. If you reduce the current, you could change it from 100 ohms to a kilo ohm, but then you need a comparator somewhere in the middle, 500 ohm or something like that, because you always need to distinguish is this higher or lower. And then you have a certain spread, so you have to ensure that you can really build, let's say, a distribution on the zero side, unprogrammed, and a distribution on the programmed side, so that there's enough room to build a comparator inside. This, but this is something which also will be explained later more in detail. So here, the same. One is intact, one is melted or semi-melted. Then you can distinguish between 1 and 0. So coming to the more sophisticated approaches, like an EEPROM, what you see here is you have to introduce, if you want to go with such an EEPROM, you have to introduce a double poly system. This is really a change in the process step. So typically you have one poly, a transistor, which you can switch on and off, and then you build in a second poly. And use the first poly not to connect it. So what you see here is really an unconnected terminal. And you use this couple capacitance here to apply a certain voltage on this terminal, which is then introducing some electrons into this terminal. And then they are there. So if once you remove the voltage, there is no force to kick out the electrons from this tunneling, and they stay there. And they're happy with that. And if you build a good isolator around, they will stay there for a long time. So that's the tricky part then, to really get these electrons on this floating gate and store it inside. And then it's more or less just, you change then a threshold of a transistor. So what you can do then is switch on a transistor and measure the current. If you change the threshold and it's a higher threshold, then the current is lower than it on a standard approach or different. And then you can build a comparator with that. So that's the easy part then to build a comparator. What you need, of course, is the comparator also suffers if you lose electrons. Of course, the threshold is going down to the original value. And this is also the nice part. There is a way to pull out the electrons so that you can come back with a threshold. So what you can do here with this floating gate is shift thresholds up and down. And then build a comparator, which is an absolute comparison of thresholds, and say, okay, threshold is higher than 2 volts or lower than 2 volts. And then you can say programmed or unprogrammed. And another technique like this, so this is a disadvantage, you need to introduce some additional poly. So this means additional process steps. This is something the fab doesn't like. So needs a requalification, needs to change thermal budgets, all other transistors will be influenced, so they have to tweak around to get back to the standard flow. So you always introduce problems with that. There are other techniques to say, okay, using a similar system, but not having a floating poly, and in newer process nodes, small process nodes, what you have is always oxide around. And I will have some cross sections later on the physical, on the how this really looks like. What you could do here is, if you could be able to get electrons in this oxide and they stuck there, you have the same like if they're floating here. You change the threshold of a transistor, and this is more or less can be seen as programmed. And then the nice thing about this trick is, if you pull down the voltage or put in negative voltages here, you can pull out the electrons up to a certain extent. There will be a kind of saturation needed for some, it depends, it's never an ideal system, so you always have some non-ideal silicon area, but once this is saturated, you can pull in and out electrons more or less easy. And this can be also used, and the nice thing about this is you don't need to change the process node, no additional thermal budget, so you can keep it as is. There will be then, the tricks will be then in the circuit around, and you need also high voltages here. But this is really also coming down to one minimum transistor size. And as said, there are much more. So coming out of the floating gate transistor, floating gate EEPROM system, what we have here. The trick about this is you need a floating gate. Theoretically, you could say, okay, if you do not connect this transistor poly here, it's also floating. And then you have to find something where you can build a capacitance with this floating poly, just to introduce, or let's say, couple a voltage here. And if you would use the second terminal on a metal, using a metal, which is typical in the flow, you have the poly, then you have the metal. You could also build a coupling. Disadvantage is, of course, a distance between an optimized poly to the next poly is somewhere in the range of a few nanometers. The distance between a poly and the next possible metal, which is the metal on top, is something around a few hundred nanometers. So what you can get here is, of course, the capacitance which you can build is related to the distance between two poles. So of course, if you increase this, the capacitance will decrease. What you can compensate this is by area. So you build huge poly gates and a couple plates. So with avoiding having a special process nodes, you increase the bit cell. Disadvantage is, of course, you end up in a few kilobits maximum range for these approaches. And this is what we call here then zero mask EEPROM, because you don't need additional masks, you can use it, but you're limited in size. You blow up your memory, more or less. But sometimes if you need just a few, let's say, 1 or 2 kilobits, this is a good compromise. Instead of changing the process node, introducing additional masks, which is increasing the price of the whole wafer, you just change the local area and take this as a good compromise in terms of costs. And then there are nice things like phase change memories. So you change really physical elements like polycrystalline phase, from amorphous phase to polycrystalline phase. This is something which needs special material. You need something which can change this. You have to apply a certain voltage to change this. Disadvantage of such system is always temperature. Then nobody were able to build a system with such elements higher than 100 degrees Celsius, because it's always recrystalling at a certain temperature. So this is more or less, but for a consumer product or a product which is in the range below, let's say 70 degrees, you could use this. It's also optimized, but additional process not optimized, but really small. And instead of using such amorphous polycrystalline phase changes, you could do it with magnetics. So there are also some memories out there having called MRAMs. Also, disadvantage of MRAMs is temperature. So also a factor of you have a certain, let's say, magnetic resistor which you could change locally, but temperature is more or less also deleting here the strength of the magnetic material, and then at a certain point the threshold is too low and then the data is gone. And to optimize this magnetic, the ferromagnetic magnetic RAM, so it's special optimized material, really big, bringing in iron into the system to improve the temperature behavior. But of course, this is something the fab doesn't like. So what you typically do is with such memories is you build up your memory plane in a CMOS fab, then ship the wafers into a different fab and build this on layers on top of your typical silicon where you store the data. So it's more or less a combined memory switch matrix where you can select these ferromagnetic RAMs. The ferromagnetic part is then somewhere far away from the bit cells. There are some suppliers out there and even products using this, but we looked into this. It's quite complicated and cost intensive. And let's say over the years we learned that the more complex you build it, the more problems you get. So better to avoid that. And finally, at the end of this session, I want to just have having a comparison between the sizes. As we said before, the size matters because it's something what you want to integrate, how many bits you want to do. Digital guys always wants to have hundreds of megabytes of RAM. And if you say use this on your microprocessor on a digital system, then you have to stop them at a certain point and say, yeah, that's plausible, or better go to a special process. So here, polyfuse, what we are talking about, just to get this line, You see, you build here the smallest line. Of course, on the other side, you build large areas where you can put in several contacts to sustain the 20 milliamps, which we were talking about before. And you have then the, let's say, the part which is intended to melt up once you program it with a certain current. If you have a logic non-volatile memory, so this is a floating gate memory, this would be, as said before, with a metal line as a coupling cup. So I just, let's say, used here schematic and would have it's not a special transistor to that, but just scaled it up in the range that you see. It's even better than the Polyfuse standalone, but quite large. A SRAM consisting of 6 transistors. It's always compared in the same, it's a 130 nanometer process node. And SRAM would be in this size, a DRAM, just as you said, just a transistor and a cup in this size. Then a flash, just consisting of the minimum transistor. So this is the transistor here. Just have the minimum distance on the poly drain source. And here you define connect or not connect. It's the easiest way. Anti-fuse is also quite small. So sometimes even smaller than the NOR flash. Sorry, this is the flash. Yes, the mask RAM. So the mask RAM is always the smallest. And the NOR flash is also consisting only of one transistor. And this part is somehow also a switching transistor. So as said here, this is coming for free in the process node. More or less this also. Here you need typically for smaller nodes 2 masks, because you tweak the process to get the optimized RAM bit cells. Here it's even more masks for a DRAM. You need to somehow define the capacitance really small, so you do trenches and build the capacitance not lateral but also vertical. So additional process steps. And then here this NOR flash, this is the optimized process for a flash. You need the more masks, and the rest is then coming without masks, ROM and anti-fuse. Okay. Let's say, just some to finalize everything. As that area is important. You have to think at a certain area size how to configure this. So typically you always have a memory. Typically, as we have always something with a factor of 2, you build 8 byte. 1 byte consists of 8 bit, or you build 2 bytes. So here would be a 16 by 16 memory array. So you have a data I/O where you can define with 16 bits, and then you need 4 addresses for that. You can also build the same. So the word length here would be 2 bytes. 8 plus 8 is 16, and the address range would be 60 addresses. 16 optional addresses with 4 bits. So, yes, built-in layout cells. Typically what you do is here, these are building blocks. So typically if you create a memory, a RAM or a ROM, you want to build a compiler, and then you want to change this on the fly for your needs. So it could be a compiler is building, let's say, creating small blocks, and also an address decoder which can change the size with certain needs. And the same memory, what you have here, is the same memory like here, but a different configuration. So here you have 8 times 32. So you have also 4 bits in address, but 1 address bit is used here to multiplex between left and right. So you just need 3 bits for the 8, 3 address bits, and 1 to distinguish between data and data I/O. And then you build a 32-bit bus. For example, ARM is using always a 32-bit architecture, so having 32-bit bus is then the direct access. You don't need to multiplex things. Or you can do data multiplexing like this. And you can also do an 8-bit system and then having additional address bits. So it's always the same address and data combination. So you see here you have 5 bits. You just use 1 additional address more, because you have also to deselect between left and right. And at the end of the day, you always get the same number of bits. Coming to more bits, you see the disadvantage of this is, of course, the address decoder is increased. it's smaller, but as there are much more addresses to connect, you always use here NAND NOR gates, so combination of 5 different inputs. So this is quite, let's say, area intensive to build. And on the data I/O, you see, you just need few data I/Os, so this is also optimized. And here you need much more bits, but you can gain some area on the address decoder. So what you can do is, for larger memories, you can try to mirror things. So use the same address decoder for the left side and for the right side, and just use one bit to distinguish block left, block right. So one address is defining left, right, and then the other addresses are decoded here. So you can build up this memory. And even for the data I/O, you can multiplex. You would have such a butterfly system, we call it then, where you have address decoders twice, but left, right, and then data multiplexes also up and down. So this is more or less an optimized one. So you see there are some options to improve. And typically what you need then at the end of the day for a digital designer doesn't care about this. This is physical, how it's ever done. A digital designer just sees memories, addresses. He sees how many bits here, how many addresses, how many data. They want to have Verilog models. They want to have simulation models. How to do. At that level, you exit. All we have seen before is more or less analog world. So you have to build a comparator, distinguish between voltages. But once you did that, you're in the digital world. And for that, you also have to prepare models. You have to prepare Verilog models. You have to prepare lib files, because typically in a digital world, you don't care about where your flip-flop is or your NAND NOR gate. This is a tool doing for you. So you have to create also a building block for this, that the tool is able to handle and place it wherever it's optimum to the next input stage to get short lengths for the data. If you have a 32-bit bus, this is crucial. It's 32-bit lines in parallel. So the closer you are to the bus, the better it is. The more area is safe in routing. So therefore you need these automatic files which your tool can handle and place it. They're called lib files, left files. And finally you have at the end of the day, you always have GTS. This is a memory block GTS data, which consists of all layers which are needed to process the memory. And just, I think the final slide for the first part is just how you use it then. This is a typical approach. You have registers, memories, whatever. You have a functional implementation. This is more or less on the digital side. So you say, okay, you have bus master, so your interfaces. Everything is done with tools. So you can build in whatever we did before, OTP, RAM, ROMs. You describe it to a level that you say, okay, I need 24 bits for this and this and this. You describe it just as a code, and more or less you do programming. Digital designer never sees a transistor. It doesn't care about the transistor. And that's more or less then the final integration. And that's far away from where we started with a single transistor. This is just then coding. That's it for the first part.